And we're recording. Okay, so last time we were talking about Green's theorem, and remember I gave you all this this sort of introductory spiel that there's a lot of sort of setup that we have to establish in advance before we can really get around to understanding what the players are that are brought together in Green's theorem. Right, and so rather than write down a theorem that you have no idea what they're even talking about, right? I want to talk about those players first, get the lay of the land established, and then we'll be able to understand what the theorem is as we write it down. And we're almost there, right? We basically are there. So quick reminder of what we did last time. We talked about boundaries now to be understood as oriented. This is a very important point. This is ultimately kind of what makes it all possible in the first place, is that we make these arbitrary, highly standard, right? Not up for discussion, but arbitrary, to be fair, conventions about what we mean by orientation of a boundary. This word boundary, now a loaded word, now an oriented thing. And we talked about the specifics, and the sort of the short version is counterclockwise, but remember, not really quite always true. The actual story is you always go whichever direction would put the region on your left. Right? That's that's what you can trust. That's what will always work. Okay, second, this idea of accumulation. Now, again, not a new idea. We've talked about accumulation a lot. Anytime you write down an integral, you are claiming that the whole is the sum of the parts, right? That's what an integral is, right, fundamentally. So we should recognize the fact that there are some quantities that have this feature, that the whole is the sum of the parts. And there are some quantities that do not have this feature. Right? And you wouldn't want to make the mistake of applying the accumulation feature to something that doesn't actually behave that way. You'd get nonsensical garbage answers. Right? Okay, for sure. Okay, so the kind of eyebrow-raising, weird, unexpected result that I'm going to claim here is that boundary circulation has this feature. Boundary circulation, geometric and abstract and non-physical though it is, has this feature. It behaves kind of like mass in the sense that the whole is the sum of the parts. Even though when you break it up into parts, you're introducing new boundary, and boundary circulation is going to be computed there, it seems like you're messing it up when you break it up into parts. But it doesn't, because on the two different pieces, the orientations are opposite, and therefore those terms cancel. Okay, so we went through a lot of that last time. Okay, so accumulation is the second big feature. And I like to point out that there's, this is just a point of view, a way of thinking about things. Specifically, the fact of accumulation. The fact that boundary circulation has this accumulation feature, that's what makes it reasonable to think of boundary circulation as being something that's happening in the interior. And this is counterintuitive because, of course, it says boundary right there in the name of boundary circulation. And so you're going to want to think of it as being something that happens here because that's where you compute it. Right? But importantly, not only do you not have to think of it that way, I think you shouldn't think of it that way. You should think of boundary circulation as something, that you talk about for an area. Given an area, you can talk about its boundary, and thus its boundary circulation. And think of it as something that happens on the areas. Okay. All right. So, very last thing we talked about was this idea of a density. Again, this is something you can do for any accumulating quantity. Right? This accumulation feature is the thing that makes this work. Because accumulation is what allows you to think of something like circulation as actually happening in a location. And thus you can talk about how much of this thing called circulation is happening within a little box and therefore you can talk about how much of that there is per unit area. You can talk about stuff per unit size, and that's a density. So this is a weird idea to get accustomed to. This definitely takes some digesting. I'm gonna be hitting this a lot. This lecture and frankly for the next couple of weeks, talking about trying to digest this idea of something, namely circulation, that's computed on the boundary as being in the interior and having an associated density. And this idea of a circulation density is computed with this formula right here. Now, again, why is that the formula? Well, there's a computation you can do, and that's in the book. And yes, it's an important computation, and the case could be made that you should look at that, but to be totally honest, it's a computation, and this is the result. And what I think is the most important is to understand sort of the big picture ideas that we've been talking about here. Namely, the whole point is that this is a quantity per unit size. Okay. Again, various bits of notation. I like to call this Green's operator, this expression right here, because it is the operator that figures prominently in Green's theorem. So this seems like a reasonable choice of terminology for me. Anyway, this is what I call it, and likewise that notation. A lot of people like to call it rote. Looks like rot. I guess you could call it rot, but the reference here is to rotation, and we'll talk about why later in this lecture a little bit. Likewise, curl. The problem I have with calling this curl is that there is another object that we're going to be calling curl. That other object has a lot in common with this thing. But that other object, also called curl, also has some very distinct and different features that does not have in common with this thing. So it gives me just a little bit of the willies to use the same word to talk about two things that I think are importantly different and not in minor ways. So I lean away from that, but this is very common terminology as well. Okay, and then in our textbook, you're going to see it written like this. So heads up, you will see this in our textbook. I don't care for it. There's a pretty significant problem here that it makes it look like there's a three-dimensional thing going on, right? Think back to when we defined curl. It's a three-dimensional thing on three-dimensional vector fields. It itself is a three-dimensional vector. Our problem's in 2 dimensions. Right, so I think this is sketchy, misleading. I think this is a problem, and I'd be more okay with it if it had other beneficial features like being compact or something like that, but it doesn't. So you'll never catch me using this notation other than to talk about how I don't like this notation. All right. Okay, but heads up, you're going to see it. Okay, so we're ready to put the pieces together. We're basically there. Here, with all these pieces established, is where Green's theorem can be thought of as coming from. So the first observation I'll make here is that we have this idea called circulation. Boundary circulation. You can see it says boundary right there. Right? So it's boundary circulation. You can think of boundary circulation as an expression to be computed, but again, and what I'm pushing here is you can think of it as a quantity, kind of like mass, kind of like any other thing that you would just give a name and a label to. So we're going to think of this as a quantity, as a kind of a stuff. I'm going to use the lowercase Greek letter sigma, very standard, to talk about this quantity. Secondly, as we discussed, this is an accumulating quantity. The whole is the sum of the parts. And so that's all this says. Right? This is our little compact integral notation for a Riemann sum, recognizing, think back when we talked about mass. If you had mass distributed over an area, right? Nobody got creeped out by saying, well, we're going to chop that up into little pieces of mass and all the mass together is the sum of all those little pieces of mass. Well, this is the same thing, just saying this accumulating quantity behaves just like mass, is the whole of the sum of the parts, and so the total is what you get when you chop it up into little pieces. You look at little pieces of boundary circulation, and then you add up over the whole region. Okay. And then lastly, recall moments ago, right? We talked about this idea of here we go, of a density, and so a little piece of circulation, you can think of that as quantity per unit area times area, right? It's like those cancel, right? So density times size gives you stuff, right? Old idea. And so that's what I have written here. You'll notice stuff is stuff per unit size times size. Does that all make sense to everybody? Does everybody see how I'm just putting the pieces together that we just already got through developing mostly last time? Okay. So here's our final result, which again would make no sense at all out of context, right? If I were to just say, oh yeah, this line integral around a boundary could be computed as a double integral over the interior of this thing. That's a formula that I write down. There's no context, right? Where is that coming from? What does that mean? What does it look like, right? Why is this thing true? Why is this assertion true? And this, I think, I find, my personal self, this is the most satisfying way to think about it. That it's true because we're talking about an accumulating quantity with an associated density. And we can add up circulation by integrating circulation density, just like we can add up and get total mass by doing an integral of mass density. Same idea. Okay, and this is called Green's theorem. So computationally, again, what it says, if you want to know how to compute a boundary circulation, an alternative computation you could do instead is a double integral of Green's operator over the interior. All righty. Let's see an example. Let's see. Yeah, okay, good. I got to zoom back in. Okay, so here we go. Hypothetical scenario. We want to compute, it says right here, a vector line integral of this vector field called F. There's F. Over this curve called C, defined here. It's the clockwise oriented unit circle. So we have ourselves a curve and a vector field. We want to compute a line integral. What do we do? Now, again, you have options, right? You could brute force this and say, I'm just going to take this vector field F, right? And I'm going to parameterize this curve, and I'm going to take a deep breath and just plow forward, right? You could totally do that. I don't recommend it. Let me sort of point out what a horrifying computation that would be. Let's just kind of think it through. How would you parameterize the unit circle? Well, sines and cosines. That means x and y are sines and cosines. Now imagine plugging that into here. X and y are sines and cosines. And it's going to get a little weird, especially right here where you'd have e to the power of probably cosine or minus cosine, depending on how you parameterize. Right, so that's not good. Okay. All right, so let's take a different point of view on this. Let's try to use Green's theorem. Recall, here we are. Here's our brand new shiny theorem. Green's theorem tells you how to compute a vector line integral. Now, here's the first landmine. The first thing you have to watch out for, the first critical little asterisk that a lot of students forget about and therefore misapply this theorem and therefore get preposterously wrong. Not only wrong answers, but unreasonable reasoning, just flat invalid reasoning. Here it is. staring right at us in this statement. This statement applies only if your curve is in fact a boundary. Right? Right there in the equation. This is not just any old random line integral off the street. This line integral has to be a line integral over a boundary curve. Otherwise, none of this makes any sense at all. And you might think to yourself, okay, well, mathematicians like to get all uptight about formalities or something, right? Not so. This has to be a boundary. Let's see here, let me use a pen. Here we go. This has to be a boundary because whatever it's a boundary of, that's going to be the domain for your double integral, right? So this is not about formalities and rigor or something like that. If a curve's not a boundary, then there is no domain to even talk about this double integral over here. So I emphasize, it's not that this and this are just different for sort of, again, subtle formal reasons. It's that if you don't have a boundary, there is no double integral to talk about. Right? Does that make sense? Everybody sort of sees the... Yeah. So, really important. If you have a line integral that's not a boundary, and you start writing down double integrals, then you're making stuff up that has nothing to do with the question. Okay, so heads up for that. Really important. So let's worry about that in the context of our example down here. Is this curve, right, the clockwise oriented unit circle? I'm only going to draw it sort of going halfway around so it doesn't mess up my picture, but I'm talking about the whole unit circle here. Clockwise oriented unit circle, is this a boundary? Now, it's going to be tempting to say yes, because after all, this curve does create the border of the disk on the inside, and tempting, right? But remember the word boundary? Loaded word. These kinds of details are really important. The word boundary now means oriented specifically in that certain way that we discussed, and this is not it. Right? So this curve is not a boundary. So we cannot use Green's theorem as it stands. Okay, what I can do is I can look at that curve, and then I can look by contrast at the exact same curve oriented the other direction. The exact same curve oriented the other direction is going the conventional direction around the border of that disk right there. So the C minus, you might call it, is a boundary. Everybody see that? So the clever move here is to say, look, we've been asked about an integral around that curve. It's going to be the negative, right? Because the orientations are opposite, right? That's going to be the negative of the line integral around this other curve, and that other curve is a boundary. What do you think? Everybody all right? Now, real quick before I go on, a lot of students look at this situation and say, okay, yeah, that just amounts to a minus sign. Minus sign is a sign error. Sign errors are like I'll lose a point or something, so I'm just not going to worry about this. Not appropriate. So let me explain what the error in that strategery is. Right? The error is to think that all sign errors are the same, and they're really, really not. Right? Now, for example, here's a sign error that we are all prone to. Right? I do this myself sometimes. If I have some algebraic expression and there's just minus signs everywhere in parentheses, it's easy to kind of accidentally miscount how many minus signs there were, and whoopsie, you make a sign error. That happens to the best of us. That's not about failing to understand a key concept, right? That's about just human fallibility. Yeah, no big deal. That kind of thing, yeah, -1, no big deal. This is not a mere little matter of human fallibility, right? If you think about it, where does this minus sign come from? This minus sign comes from recognizing that this sophisticated new Math219 idea of orientations for boundaries, right, puts us into a circumstance where I have to make this little move. I have to cite a theorem that says that when you change orientations, you get a minus sign on the value, which is a sophisticated, substantial Math219 theorem, thus allowing us to use one of the big theorems from the course, Green's theorem, right? So this minus sign here, this minus sign right here, is representative of significant, sophisticated, meaningful ideas that are really important. And this is not, again, it's not just a matter of whoopsie-doopsie, right? Oopsie, well, I counted wrong. Something like that, right? So this is a big deal. This is going to count a lot of points. I'm just telling you, right? Be warned, right? On an exam, if this were a 20-point question, getting the orientation right, probably be like 4 or 5 points. Because it's an important, sophisticated idea. And again, you got to keep in mind, that's what this course is about, right? I say it a lot, right? I'm guilty, right? But it's really important to understanding why we're here and what this course is about. This course is about ideas. That's a big idea. It's not a course about answers and whether or not you get the minus sign in the right, in the final answer. That's not what we're doing here. Okay, let me pause on that. Again, I just said a mouthful. Does anybody have any questions about any of that? Okay. Right, so moving along. We have ourselves a integral over a boundary at this point, right? We're now looking at the integral over that boundary. Green's theorem says that if you have an integral over a boundary, then you can do this right here. Notice the minus sign comes along for the ride, of course. And now I have translated the question about a line integral into a question about a double integral of Green's operator. Now another little quick aside. Is this better? Right? I mean, am I going to be more capable of computing a double integral versus a line integral? Let's just to be completely upfront about it, maybe, sometimes, right? Green's theorem is not a magic wand that turns hard problems into easy problems. Green's theorem is just a tool that turns one problem into a different problem. Right? It's kind of like a substitution, right? Just because you plug in and do a substitution doesn't mean you're helping things with an integral, right? Sometimes a substitution makes it harder. And then you're like, okay, scratch that. I got to go try something else. So don't expect and assume that this will just magically make things better. However, in this case, it totally does. Because if you look at this vector field, right, and if you compute Green's operator per the formula on the previous page, it gets real nice, right? We got lucky on this one, right? I like to start off with an example where things work well, right? So in this case, Green's theorem turns a nightmarishly inconvenient line integral into a super easy double integral. And life is good, and thank you, Green's theorem, and we get to answer this problem without having to deal with any preposterous, terrible algebra such as we were anticipating when we started on this. Is that cool? Everybody see how this is awesome? Right? Big win. Okay. All right, one more example, and then we'll go on to some related ideas. This one's a little bit weird. I like this one because it forces us to think carefully about how curves are oriented. So this is the curve we're given. It's made up of 4 line segments. This, followed by that, followed by that, followed by that. And you can see that makes this kind of triangular figure 8 sort of thing here. Now, I'm going to compute a line integral of some vector field. Fine. Here's the first thing I'm going to do. I'm going to take my curve and I'm going to break up that into 2 separate little line integrals. Same total. I'm just kind of cutting it in half. And then likewise with the next sort of diagonal piece, I'm going to break that up into two pieces. So instead of adding up 4 line segments, now I'm adding up 6 line segments. What's really nice about this, though, is that what I have here, you'll notice, these 3 of those 6, that's exactly a boundary. It's exactly the boundary of this little left triangle D1, which is awesome. Okay. All right. Let's see here. Here we go. Okay, so that's what that is. Now, here's the problem, though. If I look at the other, that looks a little too much like the gray. Let me do this in green. That's better. If I look at the other 3 pieces, and again, if you were to naively ignore orientations, and again, that's a big deal, right? It's a lot of points. It's a big, sophisticated idea that's central to what we're doing here. You might be tempted to call that a boundary as well, but of course it's going the wrong direction, right? The good news is that is the only issue. The fact that it is going the wrong direction is the only thing that's keeping this from being just literally the boundary of D2. Right? So that's why I've written the green part of what we're interested in computing as just being, well, it's just the reverse of another actual boundary. Is that cool? So we're in business. And with that noted, it's all over but the shouting, really. The curve, as noted here, my curve is boundary of D1, then the opposite of the boundary of D2. Opposite order means minus sign, right? Nothing to that. Now I have 2 integrals here around boundaries. This one I compute with Green's theorem, and this one also I compute with Green's theorem. And so this is the nugget. This is where the action happens. Rewriting these boundary line integrals, these boundary circulations, with Green's theorem, which again is what Green's theorem does. Okay, so we're going to need to know Green's operator. I'm going to have to take this vector field right here and compute Green's operator. Good deal. Green's operator just ends up being a constant again. Life is good. Sometimes, right? That vector field, easy computation. By the way, of course, it goes without saying, there's a certain amount of mechanical execution that goes into this. You had to practice and rehearse, make sure you remember the formula for Green's operator, make sure that you can implement, make sure you recall it's the x partial of the second coordinate minus the y partial of the first coordinate. Weird formula, but you got to make sure you know that. And then the rest of this calculation is easy. Notice that each one of these is an integral of a constant, specifically an integral of a constant over, high school geometry-esque geometric shape, right? Easy areas. You don't even have to compute them. The easy observation I'm going to make here is that these 2 things have the same area, so these 2 expressions here are equal to each other. So that makes the answer clearly 0. And again, I didn't have to, if you didn't have Green's theorem, you'd look at this exercise and you'd be like, oh my gosh, I'm going to have to parameterize all 4 line segments. Oh, yikes. Not that any one of them's all that bad, right? Any particular one of them. The vector field's linear, so wouldn't be that bad. But still, it's 4 separate integrals. And by some clever but powerful ideas, we don't have to do any real effort here. Cool. Everybody happy with this? Okay, here's a real slick move. I wish I had thought of it. Recall Green's theorem. Here it is. Boundary circulation on the left. Double integral of Green's operator on the right. Now I'm applying, you'll notice, Green's theorem here to a specific vector field, 0, x. This is a special vector field. It's not uniquely special, but it is a special vector field. We'll talk about what that is in just a moment. But all I've got in the green box here is just I've written down Green's theorem as it applies to that vector field. Okay. So first, let's look at what's happening on the left. This is just notation, what I have circled in purple here. This is just a recognition. Don't forget, the dx vector is dx comma dy. And you dot that out, and you get this expression right here, integral x dy. This is one of the rare circumstances where the coordinate notation is actually more compact than the vector notation. So, yeah, in this instance, I actually am kind of on board with writing it this way. It's a little bit more convenient. Make sure you're comfortable with this conversion, right? You're gonna see stuff like this, and you have to make sure that you know how it relates to the more familiar vector notation here. Okay, so what is it that's so special about this vector field? What's special about this vector field, 0, x, is that if you compute Green's operator, you get 1. That's one of my favorite numbers. It's an easy number to deal with. Easy computation. Again, make sure you can do that. Make sure you see the details there. Why does that matter? Well, the reason that matters is because if you're looking at an integral of 1, of course, no surprise, that just gives you area, right? You're literally adding up over the entire D. You're adding up 1 times the little pieces of area. Namely, you're adding up literally you're adding up all the pieces of area. That gives you the total area. Okay, so all together then, this compact little integral will compute area for you. And the surprising part of this is that the integral that you're computing is an integral around the boundary, right? It's not an integral over your interior. It's an integral around the boundary, but it computes the area in the interior. Real slick little move. Now here's a related, independent but related idea. This is just a plug and chug. I encourage everybody to do this. No Green's theorem required. This is just 6.1 argument. You can parameterize a line segment. Chapter 1 style. Parameterize that line segment. Plug and chug that line integral over that line segment. And what you will find is that the line integral, whoopsie, I was going to change the color. The line integral is computed by this formula. It's the average value of x times the change in y. So specifically, notice this right here, x1 plus x2 over 2, that's just the average of these x coordinates. So the average value of x. And then y2 minus y1 says how much did y increase from the first point to the second point. So really compact, really handy-dandy little formula. Now, these two ideas together, this and this together, give us a strategy for computing the areas of preposterous geometric shapes. So now let's think back to high school geometry class, right? You have to know the formula for how to compute the area of a right triangle and the area of a, rectangle and blah, blah, blah. What if you had to compute this area right here? I mean, it's really hard, right? And you might think to yourself, hey, you know what? I'll break this up and do a bunch of triangles. I'm going to draw extra little edges like this. And that's 1, 2, 3, 4, 5, 6, 7 triangles. I'll just compute the area of all 7 triangles. Here's the problem with that. Most of these are not right triangles. Right? So that's a really hard problem. The geometry on this is brutal. And, of course, there's 7 of them. So that's a really bad way to do this. But the argument I'm going to make instead is that, we have a corollary of Green's theorem here. If I want to compute the area, I can just do boundary line integral x dy. That's the first theorem that we just noted. Thank you, Green's theorem. And that boundary is made up of just a bunch of little line segments. You can see them right there. They're all just line segments. And on each individual line segment, on any given line segment, I have a handy-dandy little formula, just average value of x times the change in y. Bam, computes my line segment integrals. So here goes. I just have to plug and chug on this. I'm just going to do the first one. I'll let y'all fill in the remaining several. So on that first line segment right there, what is the average value of x? Well, x starts at 1 and ends at 12, and so the average is 6.5. Nothing to it, right? What's the deal with y? Well, on this line segment, y starts at 1 and ends at 6. So the change in y is 5. Again, super easy arithmetic. And as we have from this formula right there, multiplying these gives me the value of the line integral on that one line segment. So again, all you got to do is just keep going, go all the way around. It would appear that I counted 9 line segments on that outrageous geometric figure. You do the same easy calculation on each one of them, and then you add up at the end, and grand total area is 19. Way better than trying to remember Heron's formula and computing each of these lengths. It's going to be a square root. Each one of these lengths is a square root. It would be a nightmare to add up 7 triangles. It is, at most, mildly inconvenient arithmetic to do this method here. Is that cool? All right, moving along. Let's talk about flux again. Y'all remember flux. This goes back to chapter 3. The idea of flux is if you have a fluid flow, then you want to know how much of that fluid is passing through your surface per unit time. Right? This is going to be just kind of a 2-dimensional version of that. If you have not a surface but a little piece of curve here, and if you have a 2-dimensional fluid flow, like, frankly, most fluids flowing on the surface of the Earth, 2-dimensional, right? Well, the big idea then is, I might want to know what's the total quantity of fluid per unit time passing through that little piece of curve. And the general idea is very analogous to what we did in the 3-dimensional case. If you're looking for a nice little exercise to make sure you're good with how to, what the motivation of the formula for flux is, look back at that chapter 3 calculation we did. Think about how you would adapt that to a 2-dimensional scenario and kind of copycat the whole argument. 2-dimensional instead of 3, surprisingly analogous, and you'll get this as your result. So nice exercise. I encourage giving that a try, if you're in the market. Notice that all we are actually interested in is the part of the fluid flow that is in the direction perpendicular to the curve, right? To whatever extent the fluid is flowing parallel to the curve, it's not going through the curve at all. We don't care about anything happening parallel to the curve. We're interested only in what's going through the curve, namely perpendicular, and that's why we dot with this unit normal vector. Okay, here's a related idea. What if you want to talk about the flux through an entire boundary of something? Okay, so as usual, I've got some surface here. I'm not going to, some region here. I'm not going to draw the whole region. I'm just going to focus on one little piece of the boundary at a time. Right, so some region, this is just kind of zoomed in on just part of the boundary. And there's a weird little setup thing, seeming unrelated observations that I'm going to make that are going to turn out to be really handy momentarily. Let's talk about our flow vector, right, representing the fluid flow, and then the normal vector, unit normal, like that. And you can see it coming up here. Then I'm going to need to dot those. Right, I'm going to need to do a dot product of the normal and the flow vector. So I'm going to make this quick observation, real quick, that if you rotate the normal vector 90 degrees counterclockwise, you get the tangent vector. Right? Parallel is 90 degrees off from perpendicular. Okay. I'm also going to point out that you can rotate the original vector field. Now, this is a linear algebra thing. A reminder, I've said it a million times, right? How to execute a rotation of vectors is just to recognize that rotations are linear transformations. Linear transformations are represented by matrices, blah, 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 all that, stuff from linear algebra. And so good exercise, make sure you can do this. Counterclockwise rotation of P comma Q is minus Q comma P. Right? So again, make sure you can do this. If you're not sure what to do here, come on into office hours. I'll be very happy to walk you through it and make sure everybody's good with that rotation business. Next little clever observation. This pair of vectors right here, and, oh gosh, color choices. This pair of vectors right here, I claim they have the same dot product. Why would that be? And it's going to come from just realizing how dot products work. Dot products are computed by looking at the magnitudes of these two vectors and the angle between them. Well, these vectors are just rotations of those vectors. These vectors have the same magnitude as those. The angle between these two vectors is exactly the angle between these two vectors. Again, all I did is rotate both of them. So the magnitudes are the same, the angle's the same, therefore the dot products are the same. Yeah? Okay. Not clear why we're doing that. Moving along, again, as we move along our entire curve, if you want to compute the outward-oriented boundary flux through the hole, then you'd look at a bunch of little pieces of curve. On each little piece of curve, I can compute the outward-oriented boundary flux, and then I can add up over the entire curve. I get an expression that looks like that. On each little piece, using the formula from the previous page, I get this. F dot n times the length of that piece of curve, copying straight off of the previous page. And here's where all this setup work pays off. This setup work allows me to turn F dot n into this thing called fperp.t. And why does that help us? Well, having done this, I can then notice that my integral, you know what, I've kind of got a mess going here now. My integral is a dx line integral. And that allows me to rewrite this whole thing, right? This integral that I'm trying to compute, this flux that I'm trying to compute, as just a regular old vector line integral, right? None of this normal vector nonsense, right? What's the formula for the normal vector? How do I compute that? We don't have any previous theorems about this kind of a, dot in ds. We don't have any tools for how to compute that. But I've now rewritten it as a regular old, plain old vector line integral, vector field dot dx. And I have tools for how to deal with that. And in particular, I'm going to use Green's theorem here. It is a boundary circulation. I can compute it as a double integral of Green's operator. And it's all over but the shouting. So Let's see here. Let's one little tricky bit. When you apply a Green's operator, again, don't pay too much attention to the alphabet. Green's operator, right, is where you take an x partial of the second coordinate minus a y partial of the first coordinate. It's not about the p's and the q's, right? It's the x partial of the second coordinate. Our second coordinate of f perp is p, right? And then minus the y partial of the first coordinate. Our first coordinate is minus q. Zoom this in a little bit better. Right, so you get this. And move some minus signs around, and what you find is that you get exactly what we saw back in Chapter 3 we called divergence. The x partial of p, the y partial of q, that is literally the divergence of our original vector field f, and we have ourselves a new theorem. Green's theorem is about computing boundary circulation as a double integral of Green's operator. This theorem computes boundary flux as a double integral of a different operator, the divergence operator. So sometimes this is called the alternate Green's theorem, sometimes this is called the two-dimensional divergence theorem. We're soon going to see something called the three-dimensional divergence theorem. That is looks surprisingly like this, but that's going to be another week or two. Yeah.
Do you mind explaining why is the q negative again?
I'm computing Green's operator, right? But very importantly, I'm computing Green's operator of f perp, not f, right? And f perp is this thing. Is that cool? Right? And so remember, it's the x partial of the second coordinate and then minus the y partial of the first coordinate. And that first coordinate, I missed. That first coordinate is minus q. Yeah. It's how the cookie crumbles. Yeah. Okay. Oh gosh, I can't get this thing to quiet. There we go. So real quick, I'm just going to wave my hands at this example down here. This is a straight up plug and chug application where we compute this flux. We do it with the two-dimensional divergence theorem right there. And then all you got to do is just compute the divergence, plug it in, and now you've got an easy double integral. Nothing to it. I'll let y'all read that example, and we will pick up here on next time. See y'all later. Have a good weekend. Don't forget about attendance.